We're continuing our elementary study of differential forms, and let's just recall what we did last time. So last time we defined the notion of a one form and looked at a bunch of examples. So let's recall that a one form is a linear function from this tangent space at P of Rn up to just the constants r. So in other words, its inputs are vectors, n-dimensional vectors, and the outputs are just real numbers. And sometimes this is known as being a linear functional or being in the dual space of TPRn, that seen as a vector space. And then the fact that it's a linear function gives us this nice formula for it, and that is omega evaluated at this vector dx1 all the way up to dxn is necessarily of this form a dx1 plus all the way up to an dxn, where those ai's are just numbers. So our goal here is to define some sort of product of one forms, which we will denote by omega 1 wedge omega 2, and that needs to be a linear function. And that linear function has the domain TPRn cross TPRn. In other words, two copies of n-dimensional vectors. And the codomain, or the range, will be the real numbers again. And the important thing is that we want to define this product in a way so that it has a meaningful geometric interpretation. Okay, so let's look at a simple case of this setup. So let's set n equal to 2, and that means we need to define omega 1 wedge omega 2, and that needs to go from TPR2 cross TPR2 just to the space of scalars r. So in other words, we need to see what is omega 1 wedge omega 2 evaluated on this ordered pair of vectors v1 and v2. And so here v1 and v2 are each vectors in TPR2. Great, and so notice there are four things at work here. You can have omega 1 acting on v1. That'll give you just a number. You can have omega 1 acting on v2. That'll also give you just a number. You can have omega 2 acting on v1 or omega 2 acting on v2, and those are also just going to give us numbers. Okay, so let's draw a picture which will be our visual interpretation for this omega 1 wedge omega 2 acting on this ordered pair of two vectors v1 comma v2. So I want to start over here in the plane which has coordinate axes dx and dy. So in other words, this is the TPR2 plane, just kind of given from our notation in the last video. So our origin is really this base point P, and this is living in a bigger copy of R2. It's that tangent space at that point. And dx and dy, thinking back to the very first video in this series, they're really coordinate functions, but we can think about them as axes like this. Okay, now the next thing that I want to do is put v1 and v2 in this space, because we know that v1 and v2 are both in this plane. So let's say that v1 looks like this, and let's say that v2 is going up in that direction. Okay, great. Now what we want to see is what will omega 1 wedge omega 2 do to these two vectors. So maybe the first thing to do is maybe try to take these two vectors over here and transport them to two vectors in a new plane, and that's exactly what we're going to do. And that new plane we'll think of as having axes omega 1 and omega 2, where those are the two one forms. Okay. So now with two one forms, we can get a vector out of v1. So notice each of these one forms. So if you take omega 1 and you act on v1, you just get a number, because that's how these one forms are defined. And if you take omega 2 and act on v1, you just get a number as well. But if you make those two numbers components of a vector, then you can take omega 1 and omega 2 and form a vector out of acting on v1. So let's maybe draw a picture of what that would look like. So let's say that's our new vector, and it has components in this omega 1 omega 2 plane in the following setup. So we have omega 1 acting on v1, and then we have omega 2 acting on v1. Great. So again, recall that this is just a number and this is just a number. So those are the components for this vector. Now we're going to do a similar thing for v2. So that'll be a vector as well, and it will have components omega 1 acting on V2, and omega 2 acting on V2, just like we kind of did over there, but in parallel. Okay, and now let's remember what our original goal was, and that is to define omega 1 wedge omega 2 in a way so that we get a function from TPR2 cross TPR2 to R that has a geometric meaning. So we look over here at this picture we've drawn and see, can we get just a number out of this picture which we can assign to the value of this that has a geometric meaning? And I think maybe the most obvious number to look for will be the area of this parallelogram spanned by these two vectors. So let's maybe draw the rest of this parallelogram spanned by those two vectors. And I don't mean the area, I mean the signed area. So that's exactly what we'll take. So we will take omega 1 wedge omega 2 acting on this ordered pair of vectors, v1, v2, to be the signed area of this parallelogram, which I have made shaded in purple. But luckily for us, we have some linear algebra that allows us to write that down pretty easily, because we know that the signed area of this parallelogram will be the determinant of the matrix whose rows are made up by those vectors. So in other words, we know that the signed area of this will be the determinant of the matrix whose first row is this. So omega 1 v1 omega 2 v1, and its second row is given by this vector. So we have omega 1 v2, omega 2 v2. And you might say, well, why did we do it in that order? Well, we did it in that order because we're kind of working with the right-hand rule, being inspired by what's happening with the cross product, for instance. So notice if you were to cross these, you would get a vector pointing in this direction. And if you were to take the magnitude of the vector pointing in that direction would be exactly the area of this. Okay, great. So I'm going to go ahead and clean up the board. And what we'll do is start off with this summary right here, given by this wedge product of omega 1 and omega 2 is equal to this determinant, and we'll do an example. Okay, so we've derived the following formula for this wedge of two one-forms. So we have omega 1 wedge omega 2 evaluating on this ordered pair of vectors v1 and v2 is given by this determinant. So it's the determinant of omega 1 evaluated at v1, omega 2 evaluated at v1, and then omega 1 evaluated at v2, and omega 2 evaluated at v2. And the example that we gave before, we were dealing with one forms which were from R2, or TPR2, I should say, but this stands very easily for one forms that are defined on TPRN. We'll just have n-dimensional vectors here instead of two-dimensional vectors here. But that's okay, because a one form defined on TPRN evaluated at a vector in Rn will still just give us a number. So we still have a matrix of just 4 numbers there. All right, so let's go ahead and look at an example, and then we'll look at some characteristics of this wedge product. So the example that I want to look at is, let's say that omega 1 is equal to 3dx minus 2dy, and then minus dz. And then let's say that omega 2 is equal to dx plus 4dy, and let's just say that there's no dz component. Okay, and then the next thing we want to do is maybe we need 2, 3 vectors. So let's say that v1 is equal to 1, 2, negative 5. Let's say that v2 is equal to 0, 3, negative 2. Okay, great. Now we've got 4 things that we can calculate. We can calculate omega 1 on v1. So let's see what we get for that. So we'll get 3 times 1. So 3 times 1, that's because we have 3 dx. We're thinking about this as the dx, dy, and dz component. So we have 3 times 1 minus 2 times 2 minus 1 times negative 5. Great. So again, dy and dz component. So let's see what we get there. So we get 3 minus 4, which is negative 1, and then plus 5, which is 4. So we get 4 for that. And now we have omega 2 evaluated at v1. So let's see, that is going to be 1 plus 8. So that's going to be 9. And then we have omega 1 evaluated on V2. So let's see, V2 is this. So notice we're going to have -2 times 3, that's -6. And then plus 2, so that's going to be -4. And then finally, omega 2 evaluated on V2. So let's see what we get for that. So notice omega 2 only has a dx and a dy component. We have 4 times 3, so that's going to be 12. Great. And so now we have all of the parts that we need in order to calculate this. And so what we'll get, omega 1 wedge omega 2 on this ordered pair of three vectors, I should say, we'll have, let's see, this will be the determinant of 4, 9, -4, and then 12. Okay, good. But notice that's going to be 48 minus -36. In other words, 48 plus 36. So let's see, that is going to be 84. Great. So that's what we get for that right there. All right, great. I'm going to go ahead and clean up the board, and then we'll look at some characteristics of this wedge product. Okay, so we've just looked at an example, and now we want to go through some observations involving this. And the first one is pretty nice, and that is if you take omega 1 wedge omega 2, you get negative omega 2 wedge omega 1. And so now, since I haven't put any inputs here, that means that something like this has to be true for all inputs. So let's go ahead and see how this works. So let's suppose that we have V1 and V2 in TPRN, and these are arbitrary. And what we want to do is calculate omega 1 wedge omega 2 evaluated at this. So we know omega 1 wedge omega 2 evaluated at this ordered pair of vectors is given by that determinant up there. So that's going to be the determinant of omega 1 evaluated at V1, omega 2 evaluated at V1, omega 1 evaluated at V2, and omega 2 evaluated at V2. Great. Now the next thing that I want to do is swap columns. In other words, we're going to do a column operation. But if you recall from linear algebra, whenever you swap two columns of a matrix, you end up negating the determinant. So that means I can put a minus sign here and then swap the columns. So that's going to give me omega 2 V1, omega 1 V1, and then down here I have omega 2 V2, and then omega 1 V2. Great. But now, kind of working our way out of that hole, we notice that that determinant is exactly omega 2 wedge omega 1 evaluated at V1, V2. And then since V1 and V2 were arbitrary, what we've shown is that omega 1 wedge omega 2 is equal to negative omega 2 wedge omega 1 as functions. So we have this anti-commutativity here. Okay, and then similarly, and I won't work out the details for this, but similarly we have omega 1 wedge omega 2 evaluated at V1, V2 is equal to negative omega 1 wedge omega 2 evaluated at V2, V1. So if I swap the order of my inputs, I also pick up a minus sign. And that's done with essentially the same proof, except instead of doing a column swap, we're going to do a row swap. Okay, and now one more thing before we kind of clean up this board and do something else for the video, and that is if you have omega 1 wedge omega 2 is negative omega 2 wedge omega 1, well then that immediately implies that omega wedge omega is equal to negative omega wedge omega. So in other words, this function, which is the wedge product of a one form with itself, you can do that commutativity and you'll end up with the negative. So a function is equal to a negative, but there's only one function that satisfies that, and that's the 0 function. So we have omega wedge itself has to be equal to 0. Okay, I'm going to go ahead and clean up the board, and then we're going to look at a special case of this product for TPR2. Okay, now we're going to look at a really special case, and that is when we're dealing with one forms on TP-R2, in other words, on the tangent space of R2. And if we've got two one forms, omega 1 and omega 2, in that space, if we take their wedge product, omega 1 wedge omega 2, we get a constant times this very special product of two one forms, which is dx wedge dy. And I should say here for some number c, which is a real number. So let's go ahead and see how the proof of this goes. It's really just calculation built off of our last observation. So let's maybe say that omega 1 is equal to a dx plus b dy. And let's say that omega 2 is equal to c dx plus d dy. Okay, now we have omega 1 wedge omega 2. So that's going to be equal to a dx plus b dy wedge c dx plus d dy. And now I'm going to cheat a little bit and do something that I haven't proven, but it's pretty easy to prove, and I urge you to do that as an exercise. And that is that we have a nice distributive rule for addition of one forms and this wedge product of one forms, making it possible to like essentially FOIL this product out. So let's go ahead and see what we get if we do that. So if we take a dx wedge c dx, that's going to be a c dx wedge dx plus, and now the next thing we have is a d dx wedge dy. And then the next thing we have is b c dy wedge dx, and then the last thing we have is b d dy wedge dy. But then from our last observation, we know that dx wedge dx and dy wedge dy are both 0 because those are just very special cases of a one form wedge itself. And then we know that dy wedge dx and dx wedge dy are just opposites of each other. In other words, one is the negative of the other. So we could swap the order of dy and dx here and just pick up a minus sign. So that's going to give us AD minus BC. And now we have dx wedge dy. And so what I've done is I've just swapped the order of this, picking up a minus sign here. Okay, great. But notice that this is just a number times dx wedge dy, which is exactly what we wanted to do. So now it really like begs the question is, what is this special one form dx wedge dy? And so I'll clean up the board, and that'll be the last thing that we do for this video. So we just got done proving that if you take the product of any two one forms on TP-R2, you get a scalar multiple of dx wedge dy. And so that really like begs the question is, what is the product of these two one forms? And this is actually an example of something called a two form, this kind of object. Or really, anytime you take a product of two one forms, you get something called a two form. But we're going to more carefully define that a bit later. But we just want to see, in the language of what we're doing here, what is the product of this one form dx and this one form dy? Well, before we get to it, let's just kind of recall what these things do. So notice if we take dx and we attack some vector, and so let's say we're inserting the vector a1 comma a2 in here, well, that's just going to give us a1. So in other words, it just kind of pulls out the first component. And then similarly, if we take dy and we attack the vector a1, a2, we're just going to get a2. So in other words, we pull out the second component. Okay, great. So now let's suppose that we have two vectors. Maybe we'll call one v, which is a1, a2. And then let's call the other one w, which is equal to b1, b2. And what we really want to do is see what dx wedge dy does to v comma w, because recall, since this is a product of one forms, which we'll later call a two form, it needs to have two entries into it. And so in other words, we want to look at dx wedge dy on this ordered pair of vectors v comma w. Okay, fantastic. So let's recall that that needs to be the determinant of dx on v and then dy on v. and then dx on w, and then dy on w. But now taking dxv, dyv, that really just puts a copy of the vector v in the first row of this matrix. That's pretty easy to see because dx on this takes out the first component, dy on this takes out the second component. And then the same thing down here. dx on w and dy on w just gives us w down here. But notice that that is just the signed area of the parallelogram defined by v and w. So that is the geometric interpretation of this dx wedge dy. And you'll see that if we boost this to higher dimensions, we get a similar geometric interpretation, which we'll explore in further videos.